Hello everyone. In today's video, the topic of discussion is displacement current. So, in the field of electromagnetism, you will find this displacement current, and you know that there are so many laws. Actually, 4 laws are there, which are known as Maxwell's law, Maxwell laws. Okay, 4 laws are there. First 2 laws belong to Gauss, and third one belongs to Faraday, fourth one belongs to Ampere, but later the fourth law, means Ampere's law, was corrected by Maxwell himself, James Clerk Maxwell, by the introduction of the new entity, displacement current. So question is how the correction was made and why the correction was made, means what was the necessity of making that correction. That is the question. Okay, so you know Faraday's law. According to Faraday's law, this relates a magnetic field and electric current. Changing magnetic field induces electric current, or changing magnetic field creates electric current. That thing we can know from Faraday's law. And according to Ampere's law, without Maxwell's correction, only Ampere's law, according to Ampere's law, changing electric field creates magnetic field. Okay, changing electric fields create magnetic field, or you can say this way also, changing electric fields create changing magnetic field. Anyway, so this law belongs to what? Belongs to whom? This law belongs to Ampere. You can see all the equations on the screen. So according to this, J is there, J is present, again that magnetic field is present, where B represents magnetic field, okay. But for steady flow, means for steady current, flow means a flow of charges. I was talking about flow of charges. That means steady current. For steady current, there is absolutely no problem with Ampere's law. There is no problem. It is 100% valid. Ampere's law remains 100% valid for steady current. But when the current is not steady, when there is changing electric fields, such as if you take the example of a capacitor, you know that in between the capacitor plates, dielectrics are there. And through dielectrics, current cannot flow. So that means when a capacitor is being charged or discharged, electric fields are present due to the positive and negative charges on both the plates. On one plate there is negative charge and on another plate there is positive charge. But in between them, what is there? Dielectric is there, but there is no flow of current through that dielectric. That means conduction current is absent. Conduction current remains absent when the capacitor is being charged or discharged. In both the cases, whether it is being charged or being discharged, in both the cases, changing electric fields are present. So, if you now look at the equation proposed by Ampere, then you can see that there is a discrepancy, because conduction current is absent, but still magnetic field remains present. Why magnetic field remains present? Because changing electric fields are there. In case of capacitor circuit, changing electric fields are there because it is being charged, the capacitor is being charged or being discharged. So electric fields are there, but conduction current remains absent. So to make the necessary correction, James Clerk Maxwell introduced the idea of a new entity known as displacement current. Though practically displacement current is not current in conventional sense, because there is no flow of charge carriers. There is no flow of charge carriers between the plates through the dielectric. There is no physical movement of the electric charges. That's why the new name is given to this effect as a displacement current. And this displacement current term, this is given by everything you can see on the screen. This displacement current is given by that quantity, epsilon 0 into d phi e dt. Okay, where phi e is the electric flux, t is time, and epsilon 0 is there, and that is permittivity of free space. So this way, the idea of displacement current came in the mind of Maxwell. So this way, the law was corrected. Law of Ampere was corrected, and the new name is given as Ampere-Maxwell law. This is the new name, Ampere-Maxwell law or Ampere's law with correction. Anyway, after this discovery or after the introduction of displacement current, one more thing, that is the most interesting thing, according to Maxwell, changing electric fields creates, changing electric fields create changing magnetic field, and changing magnetic fields create changing electric fields. That means both the electric fields and magnetic fields, they can sustain each other even in free space, and that way that idea gives rise to the concept of electromagnetic waves. And later we came to know that light itself is electromagnetic wave. Light itself is an electromagnetic wave, and all other waves, radio waves, or in case of Wi-Fi, anything. Here, all these things are electromagnetic waves, whether it is visible light or not, but all these things are electromagnetic waves. And for that discovery, okay, actually the discovery was made by whom? Made by Maxwell, after that correction. Okay, this discovery was made by Maxwell, and later you know everything, that without those discoveries or without that particular discovery, today's world would have looked different. Okay, because if means we should thank to Maxwell for his discovery, for which all these things have become possible today, such as internet, Wi-Fi, etc. Means wherever there is a use of electromagnetic waves. Okay, because the idea came into the mind of Maxwell just after making that correction, that is the displacement current. So once again I want to repeat the same thing, that displacement current is not actual current, means is not current in the conventional sense, because there is no movement, there is no motion of electric charges. Okay. Anyway, so this was all about today's topic, and this is the end of this video. If you found this video to be fascinating, then please like, share, and subscribe to our channel. Anyway, so this is the end of this video. Thank you for watching this video.